Signal processing practice final exam part 4, number 9. Random process has the autocorrelation R sub x of tau equals 10 e to the negative 2 times the absolute value of tau. Part A, determine the average power. So this is random signals and noise. So the average power R sub x of tau equals 10 e to the negative 2, absolute value of tau. Average power is autocorrelation at zero lag. P sub x equals R sub x of 0. So P sub x equals 10 e to the 0. So that equals 10 times 1, which is 10. So P sub x equals 10. Part B, find the power spectral density. So the power spectral density, PSD, is Fourier transform of autocorrelation, known transform here. So here A equals 2. E to the negative 2 absolute value of tau equals 4 over 4 plus omega squared. Multiply this by 10. S sub x of omega equals 40 over omega squared plus 4. So that's S sub x of omega equals 40 over omega squared plus 4. Part C, determine the total energy. So the total energy, a random process with non-zero average power, generally has infinite total energy over infinite time. Let's see if this holds up. And now for part D and E. For part D, find the correlation time. Part C was determining the total energy. Part D, find the correlation time. Correlation time, exponential decay constant is 2. So the characteristic correlation to time is tau sub c equals 1/2. And part E, interpret the physical meaning of exponential decay. Physical meaning here. The correlation decreases as lag increases. Values separated by time much larger than 1/2 are weakly related. The process loses memory over a time scale of 1/2. Okay, so that's number 9. Okay, number 10. Okay, so let's see. So focus. So we have a desired signal here, S of n. Observed signal x of n equals S of n plus V of n, where the noise is white Gaussian with variance sigma sub V squared equals 4. Signal or autocorrelation R sub s of k equals 9 times 0.7 to the absolute value of k. Part A, find the signal PSD. So this is Wiener filtering estimation theory. So part A, or noise variance, sigma sub V squared equals 4. Signal autocorrelation R sub s of k equals 9 times 7/10 to the absolute value of k. The known dt ft result is this transform A to the absolute value of k, and that transforms to 1 minus a squared over 1 minus 2a cosine omega plus a squared, where a is 7/10, R sub s of k equals 9 times 0.7 to the absolute value of k. So S sub s of e to the j omega, that's going to be 9 times 1 times the quantity 1 minus 7/10 squared over 1 minus 2 times 7/10 cosine omega plus 7/10 squared. So wind up with 1 minus 0.49, that equals 0.51. So S sub s of e to the j omega, that's 4.59 over 1.49 minus 1.4 cosine omega. So our white noise with variance 4 has flat PSD. So our S of V, I'm sorry, that's part A. I went too far. So here we have part A, signal PSD. Part B, find the noise PSD. So part B, the white noise with variance 4 has flat PSD. So S of V of e to the j omega, that equals 4. Part C, construct a Wiener filter. So for part C, for estimating S of n from x of n equals S of n plus V of n with uncorrelated signal and noise, H sub here, this value equals S sub s of e to the j omega, sorry, over S sub S e to the j omega plus S sub v e to the j omega. So our h sub w here equals S sub S of e to the j omega over S sub S e to the j omega plus 4. For part D, determine the transfer function minimizing MSE. Substitute h sub w of e to the j omega equals the following: 4.49 over 1.49 minus 1.4 cosine omega over 4.59, sorry, over 1.49 minus 1.4 cosine omega plus 4. Multiplying the numerator and denominator by 1.49 minus 1.4 cosine omega. At the end, we get h sub w of e to the j omega equals 4.49 over 10.55 minus 5.6 cosine omega. Part E, explain why Wiener filter is optimal. So part E, the Wiener filter minimizes the mean square error given here among all linear time invariant estimators. It weights each frequency according to signal to noise ratio, where the signal dominates noise, h sub w is approximately 1. Where the noise dominates the signal, h sub w is approximately 0. It is optimal in the linear MMSE sense. Okay, so that is number 10. Number 11 here. So we have a DFT. Whoops. Number 11, a DFT of length n equals 1024 must be computed. Determine the number of multiplications using direct DFT. Determine complexity using radix 2 FFT. Compute the speedup factor for letters C and D. Explain the divide and conquer principle. So this is an FFT algorithm complexity problem. So for part A, determine the number of multiplications. N equals 1024. That equals 2 to the 10th. So the direct DFT requires an approximation of n squared complex multiplications. So 1024 to the second gives you 1,048,576 complex multiplications. For part B, determine the complexity using radix 2 FFT. Radix FFT requires approximately n over 2 log base 2 n complex multiplications. So that gives you 5,120 complex multiplications. For part C, compute the speedup factor. For the speedup factor, that's just going to be 1,048,576 over 5,120. So you get about 204.8, which is about 205x. And part D, explain the divide and conquer principle. So for part D, the FFT splits the DFT into even indexed and odd indexed samples. So x of k is this summation. We separate into even and odd n for x of k equals the following. Summations summed. And since w sub n to the 2k equals w sub n over 2 to the k, the DFT becomes two smaller DFTs of length n over 2. So the FFT recursively reduces one length n DFT into two length n over 2 DFTs. Okay, moving forward, that was number 11. Number 12. Okay, consider the system x dot equals ax plus bu, where we have a equals 0, 1, negative 4, negative 3 for those rows respectively. B equals 0, 1 for that column. Part A, find the eigenvalues. Part B, determine the stability. C, find the matrix exponential. D, determine the transfer function. E, determine controllability. State space signal representation problem. So for this, x dot, we take what we're given. We're going to assume the output y given here. So C here, D equals 0. Eigenvalues, just take that determinant of lambda I minus a, set it equal to 0, and we're going to get the following for our lambdas. And for part B, stability, determine the stability. Stability is the real part. Negative 3 over 2 is less than 0. So asymptotically stable. Part C, find the matrix exponential. The matrix exponential for a 2 by 2 matrix with complex eigenvalues, we write alpha is equal to -3/2. Beta is square root of 7/2. And then we get e to the at equals e to the alpha t times this quantity I cosine beta t plus a minus alpha I over beta sine of beta t. So a minus alpha I equals a plus 3/2 I equals this matrix here, 3/2 and 1 for the first row, -4, -3/2 second row. So we're going to get e to the at equals e to -3t/2, bracket I cosine square root of 7/2t plus 2 over square root of 7. First row matrix, 3/2 1. Second row, -4, -3/2 sine of square root of 7/2t, close bracket. Part D, determine the transfer function. Well, the transfer function h of s equals this. Okay, so si minus a equals this s -1 first row, 4s plus 3 second row. Its inverse here is 1 over s squared plus 3s plus 4. S plus 3, 1 first row, -4s second row. Multiplying by b, we get 1 over s squared plus 3s plus 4, column 1s there. Multiply by the c. H of s is 1 over s squared plus 3s plus 4. And for part E, determine the controllability. Controllability matrix is C equals B, AB. B equals this 0, 1. So AB, that's going to come out to 1, -3. C, 0, 1, 1, -3. So our determinant of C, 0 times -3 minus 1 times 1. That's -1. That does not equal the 0 for that determinant. So the system is controllable. Okay, so that's number 12. And number 13. A noisy signal consists of two closely spaced frequencies here for x of n, whose noise is Gaussian. Part A, explain why standard FFT may fail. So this is DSP and spectral estimation. So the FFT frequency spacing is delta omega equals 2 pi over n. And if this absolute value of omega sub 1 minus omega sub 2 is less than the change in omega, then the two tones may fall within the same FFT bin or adjacent bins with overlapping main lobes. Noise and spectral leakage further obscure the two peaks. FFT may fail when frequency separation is below its resolution or when there's leaking or noise making. Part B, derive the periodogram estimator. So periodogram estimator for the data given here. We define the finite length for DTFT as the following. X sub n of e to the j omega equals this summation. So the periodogram is s of x hat of e to the j omega equals 1 over n magnitude of x sub n of e to the j omega squared. So at the DFT frequencies, omega sub k equals 2 pi k over n. So we wind up with s sub x hat of k equals 1 over n times the magnitude of x of k squared. Sorry. Part C, explain spectral leakage. Okay, so for part C, spectral leakage, a finite observation window multiplies the infinite signal by a rectangular window. Time domain multiplication corresponds to frequency domain convolution. Therefore, the true spectral lines are smeared by the transform of the window. Spectral leakage is the spreading of spectral energy caused by finite windowing. Part D, compare Hamming, Hahn, and Blackman windows. So comparing the windows, rectangular window, narrowest main lobe, highest side lobes, and best resolution but worse leakage. For Hahn window, lower side lobes than rectangular, wider main lobe, and good general purpose choice. Hamming window, similar to Hahn, often slightly lower first side lobe and good for reducing leakage. Blackman window, much lower side lobes, wider main lobe, and better leakage suppression, but worse resolution. Window choice trades frequency resolution against leakage suppression. And for part E, explain why parametric methods, AR modeling, music, Esprit can outperform FFT. Okay, so FFT is non-parametric and limited by data length and bin spacing. Parametric methods assume a signal model. For example, music and Esprit assume a sum of sinusoids plus noise and use the eigenstructure of a correlation matrix. Because they exploit model structure, they can resolve frequencies closer than the FFT bin spacing under good SNR and correct model order. Parametric methods can achieve super resolution when their model assumptions are valid. Okay, so that's part 4, and that's all for this practice exam. Thank you and have a great day.